So I would like to thank the scientific committee for inviting me to give this work, which is going to be a recollection of what's been done over the last whatever number of years on credible regions and asymptotic for credible regions. And the last things are joint work with Boton-Sabot and Jean-Bernard Salomon. So first I'll describe sort of the setup, Bayesian, credible regions, what we do with that, and the kind of questions we've been wondering in high dimensions. So there are a number of things that happen in high dimensions, and it's much more subtle than actually you think about. And so somehow that sort of points towards being cautious about the kind of model that you use, somehow. That's my take of it. So just general setup is just to give notations, although it's quite possible the notation are going to change over the slides. But the idea are that you have data y or x depending on the slides, and that theta is usually going to be the parameter. I think that's fairly stable, and pi is going to be the prior or the posterior, pi given x or y. And so we're going to have dominated models. So the posterior distribution, the conditional distribution of theta given y, is proportional to the prior times the likelihood. And as you all know, when you do Bayesian inference, this posterior distribution drives the whole story. Yeah? And so if you understand the posterior distribution, then you understand a lot of things. And that's sort of the aim of the game. And so what can you do? Well, you can do point estimation, of course. You can do prediction as well, all that from the posterior distribution. And you can also have natural measures of uncertainty, which are either risk estimation or credible regions. And that's sort of the focus of the talk here, which is how do we understand the behavior of credible regions. And now you can do tests and model selections, and although there is a flavor of that in this talk, it's not going to be the focus of the talk. And so here, when you're in high dimensions, the prior becomes important, and more important actually. And so the question is, what are the sort of aspects of the prior that you need to be careful about? And typically these aspects are aspects that do not disappear asymptotically. And that's sort of the idea. And so whatever doesn't disappear asymptotically, you really have to be careful about them. So because I'm going to talk about, and so also one of the key points when you look at credible region, one of the key tools, which is like an old tool, is the Bernstein-von-Mises result, which I'm not going to talk about, except at the beginning, for slow dimension. So what's the Bernstein-von-Mises result? So I'm going to illustrate it in dimension 1. So imagine that you have a Poisson distribution with parameter theta, a gamma prior on theta, then you have a gamma posterior. And the Bernstein-von-Mises result tells you that asymptotically, so these are different n equals 1, n equals 10, and n equals 100. As n increases, the posterior becomes more and more concentrated and looks more and more like a Gaussian distribution centered at something. And more formally, what it means is that if you're looking at the posterior distribution of theta minus the MLE, or the posterior mean, then this posterior distribution, when you rescale by square root of n, in finite models, finite dimensional models, asymptotically looks like a Gaussian distribution with variance, which is the frequencies variance of the centering point. So when you have something like that, then you have what's called the Bernstein-von-Mises results. And you can formalize it also by looking at the L1 distance between the posterior density and the Gaussian density, and it has to go to 0. So that's exactly the Bernstein-von-Mises result, and when you have that, then you're happy. And the reason why you're happy is that if you have a Bernstein-von-Mises result, then any no sort of usual credible region is going to be also a confidence region. In other words, if you have a credible region for which the posterior distribution is equal to 1 minus alpha, something like a credible interval, or a credible HPD region or something like that, then for all theta, it's also going to be a confidence region. And then what it means is that somehow your measure of credibility, or the way you construct your credible region, is going to be robust to the choice of the prior asymptotically, because the prior disappears to a high order asymptotically. And the question is, and it's also useful for a computational point of view, but that's not the point here. And so the question is, how can you sort of extend these ideas in high dimensions? Do they stay the same, or do you run into troubles? And what kind of troubles do you face? So the kind of regions I'll be looking at here are credible balls. So which means that, so this is a credible region. In other words, the posterior probability of this region is 1 minus alpha. And then I'm looking at a ball, so I take a centering point, so it could be the posterior mean or the posterior median or whatever. And then I'm looking at a set of theta, such that the distance between theta and this centering point is smaller than a function of the data. And Q alpha of xn is determined by the fact that the posterior probability of this ball is 1 minus alpha, or at least like 1 minus alpha. So let's say it's equal to 1 minus alpha. So now that's a Bayesian construction here. And the frequencies question would be now, what's the frequencies confidence in this region? Which is what I had before, like if I had Bernstein families, and I would know that the frequencies confidence would be also 1 minus alpha asymptotically. Now the question is, if I am in high dimension, I may not have Bernstein families, but can I say something about the confidence of this region, the frequencies confidence of the region for all theta uniformly? And the second kind of question I'll be looking at is the size of the region. So how large is my region? Because if I choose Q alpha of xn to be infinity, then of course I have a good confidence, but I have absolutely no precision. And so what I want is to have the smallest possible regions, but with the highest possible confidence. And that's a balance between the two. And hopefully that's what happens in a story. And the question is really now you're in high dimensions, the prior doesn't completely disappear, and what's going on? So what do I mean by high dimensional models? I'll be looking at non-parametric standard models. I'm just giving here a bunch of examples, but they are not the only one, of course. So you can have a non-parametric regression, where xi belongs to a finite dimensional like 0, 1 to the power d. And then in this case, the parameter space is a space of L2 functions, so square integrable functions on 0, 1, d, for instance. You could have also non-parametric classification, so same story, so where you have a logic link function, and then your parameter theta is still, again, this f here, and it still belongs to L2. That's one possible sort of a set of assumptions that you can put on the parameter space. And you can also have a high-dimensional model, so it's parametric, but it's high dimension. So high-dimensional linear regressions, like that, so there's a famous one, where p is typically greater than n. So these are like typical high-dimensional model I'll be considering, either standard non-parametrics or high-dimensional parametric models, like that. And they share common features. Not all of them, but they share common features. And so so the question is, how do you put a, where am I? Somewhere here. So the question is, how do I construct a prior on these sort of spaces? Well, there are lots of ways to do that. You can put Gaussian process, for instance, on these guys. You can put, if you were to estimate the density, you could put a Dirichlet process mixture. I mean, there are all sorts of things I can do. Now, if you have, now what we're going to look at are measures of uncertainty. So the credible balls I was talking about. So we have a region so that the credible or the Bayesian coverage is equal to 1 minus alpha. And even without effort, you can still say something about the frequencies coverage. And that comes from a Fibini argument, so it's very simple. If you have a credible region like that, then what Fibini tells you is that on average, if you integrate with respect to the prior, so the same prior that you use to construct the region, if you integrate with respect to the prior, on average, then you also have a confidence region. And so the question, the first reaction would be, well, that's good enough because I'm good on average. So why should I worry about being good uniformly, especially given that I'm optimal from a Bayesian perspective? The reason why you have to worry about it, I think, is because when you are high dimensional like that, typically your prior, I mean, for those who haven't heard the story before, the prior puts mass on a very small set of theta. Although the support of the prior is the closure of a small set, so it's a large set. So theta being L2 can be the closure of the support of it can be the support of the prior. It actually still lives in a very small set. So for instance, imagine that you take as a prior, you truncate you take a parameter that's a function in L2, you expand this function on a basis, and then you truncate your function at a random k. For each k, your support of your prior is a parametric space, okay? And so the support of the prior is very small compared to the whole space. But the support, I mean, the closure of the support is a closure. But the support of the prior is big, but the prior lives on a small set. And that means that when you're taking the average here, you could be actually hitting points that are very rare. And so it doesn't tell you anything about the standard behavior of a theta that you would pick with a different prior. So if someone came with a different prior, he might have completely different average from what you have using the prior that you use to construct the credible region. And that's worrying, because it means that if you have two different priors, two different Bayesians, they'll give you completely different measures of uncertainty. And that's what we want to sort of understand. What kind of priors give you more robust measures of uncertainty? Or if they don't, why, and how can you understand them somehow? So that's one thing. So that the coverage is one worry to have. The second is the size, as I said before. So how can you understand the size? So as I said, the size is really the radius of the ball. So this Q alpha x here. And the question is, how can we easily get measures or control on these sizes here? Now, the nice thing about it is that, yes, there is an answer. It's easy to prove that if you have a posterior concentration rate type of result, and I'll go back to it to explain what it means, then you can control the size. And what's nice about it is that there is now a large literature on posterior concentration rates. So we know fairly well how to deal with that, and so we don't have to invent new tools to understand the behavior of the size of the balls, the credible balls you're considering. So what do I mean by posterior concentration rates? I'm talking, it means, I mean that you're looking at balls around the true value of the parameter, theta naught, such that are shrinking at a certain rate, epsilon n, and you want to select epsilon n as small as possible, but still such that the posterior mass of this ball goes to 1 as n goes to infinity. Okay? So you're looking at shrinking balls toward the true value of the parameters. And the rate at which the balls shrink, this epsilon n, but we're still having posterior probability going to 1, this rate gives you the posterior concentration rate. That's what we call the posterior concentration rate. And what the story tells you is that if you have a posterior concentration rate of epsilon n, and if your centering point of your credible ball is good enough, let's say, I'm not going to describe more what it means, then the size of the ball is going to be also of order epsilon n. Okay? So if you understand the posterior concentration rates, then you understand the size of your ball. And what's nice is that now there is a large literature on posterior concentration rates.
Is the size of x fixed? Size of x?
I told you the data is going to change all over. So the x depends on n. Yeah, so x is the xn. So yeah, so the n here is the sample size typically, or the information in the data. And so as n goes to infinity, when the sample size goes to infinity, the posterior moves, varies, but it has this posterior probability of this ball has to go to 1. Okay. And so then, in other words, it's going to shrink towards the true value of the parameter, so it's going to learn the true value of the parameter at a certain rate. That's what it says. So there is now, as I said, there is now a large literature on posterior concentration rates, and they are not so modern. They date from the work of Le Cam and Lawrence Schwartz, and then later on by Andrew Barron, where they sort of they paved the way to analyze these posterior concentration rates by looking at essentially at consistency, but it's essentially the same story. And then in the early 2000s, Gozal and van der Waart, and Gozal, Gosch and van der Waart had their sort of seminal papers where they gave a list of conditions that are fairly easy to verify to get a posterior concentration rates. And that allowed the literature to sort of grow hugely from that. And now there is a huge number of papers. I mean, huge, maybe I'm exaggerating a bit. But there is a large number there is a large number of papers where they've studied different models, different families of priors, all that together. So we know how to do that sort of things, essentially, almost. So and the general strategy is to look at two different type of things. One is to look at the prior mass of Kullback-Leibel neighborhood, and the second is to look at the existence of tests. And the reason why I've put the test here in blue is not because it's specific, it's just because the existence of tests is linked strongly to the distance d that you're considering when you're looking at the ball. So this distance d in the story cannot be anything if you want to apply the strategy of Gozal, Gosch, and van der Waart. So it only works with certain distance d's, And I'm going to go back to it slightly later. That's what I said. And now, and also, if you these were sort of there is a large number of work now on non-parametric base, but also on high-dimensional models, and they essentially work the same so long as you're considering distance metrics here D that are well behaved, and so that means that these tools are really powerful to tackle a large number of problems. Unfortunately, it only gives you information on the size of your credible region and not on the coverage of your credible region. And so it only gives you part of the story. And if you want to understand the coverage, then you have to do a lot more work. And that's what I'm going to talk about now. One of the advantages of the Bayesian analysis or Bayesian modeling is that you're naturally hierarchical. Because you have a prior that depends on hyperparameters, and then if you don't know how to choose a hyperparameter, then you construct another prior, and so on and so forth. You can go as far as you want there. And that gives you a lot of flexibility, and this flexibility drives or leads to adaptive methods. So you can adapt to all sorts of things. And so what I mean here in this talk, we're going to look at adaptation in terms of minimax adaptation, but you could adapt to other things. So what do I mean by adaptive Bayesian methods? I mean the following. Imagine that you have a parameter space which can be written as a collection of different parameter spaces. For instance, if you are in L2, you could decompose L2 as Sobolev spaces where the coefficients decrease to 0 at a certain rate. Okay? And the rate at which the coefficients decrease to 0 sort of gives a notion of smoothness on your parameter. Okay? And so for each beta, you have a different space here, and the collection of the reunion of these spaces is a whole parameter space. Okay, so L2 can be approximated by the collection of these guys, and now you don't know beta in truth. You don't know the smoothness of your true parameter. So what you want to have is you want to have an estimator that doesn't depend on beta, but still does good for every parameter that which belong to theta beta. Okay. What I mean by good is that if you knew beta, then you would be assuming purely that theta belongs to this set or to a ball which is within this set. Then you would get a minimax rate to estimate that from a frequentist point of view, which I call epsilon n of beta. And this being good means that the rate of estimation for estimating your parameter in this class has to be as good as epsilon beta. Now what you want to have is an estimator or a procedure, whatever that is, such that even though you don't know beta, it's still doing as good as if you knew beta. Okay, for all beta, you're going to be as good as if you knew beta, but you don't know it. So that's the frequentist adaptation, and the Bayesian adaptation is a similar story. If you were to look at posterior concentration rates, you said that you have an adaptive posterior concentration rate if the rate of concentration depends on beta, even though your prior doesn't depend on beta. So you have a Bayesian procedure that's free of beta, that doesn't depend on this smoothness that you don't know, or the sparsity of your parameter that you don't know. But still, somehow you learn the smoothness by the data, and for all parameter in the parameter space theta beta, then the rate of concentration is bounded from above by epsilon n of beta. So you have an adaptive procedure in this context, and you are adapting in the frequentist sense using a Bayesian tool. That's the way to think about it. And Bayesian approaches, because they're hierarchical, are naturally adaptive. You can really, and it's very easy, and all these papers in the literature show that it's easy to build up procedures that have adaptive posterior concentration rates, just by adding up piles or layers in your hierarchy. So for instance, if you take a Gaussian process, and typically it's not non-adaptive, but if you take a hierarchical Gaussian process, there are ways of constructing the hierarchy, then you get adaptive procedures over Hölder spaces or Sobolev spaces. If you take non-parametric mixtures, they are naturally adaptive as well, by putting some priors on some of the hyperparameters and so on. And if you take a nonlinear regression, for instance, and you don't know the sparsity of your parameter, you don't know how many coefficients you should take in your model, then by putting a correct prior on this number of coefficients, then you also can learn the sparsity of your model, and so you are adapting again. Okay, so that's all this sort of, and it's true in many, many contexts. So it's great because you're saying, wow, we are really have these sort of nice tools to get adaptation by just the possibility of having hierarchical models. There must be a price to pay, and unfortunately there is a price to pay. And the price to pay gets in the confidence. And I'm going to explain why. And it's not because you're Bayesian, it's because it's a price to pay from an existing point of view, somehow. So if you are now interested in confidence regions, what you want, as I said at the beginning, what you want is a region that's small, but still have large confidence. Okay, so you want a small size and large confidence. So when you have large confidence, it means that you are honest, and if you are honest, if you're uniformly large, in a sense that the infimum over the parameter space of the frequentist coverage of the space is bounded from below by 1 minus alpha. That's an honest 1 minus alpha confidence region from a frequentist point of view. And you're adaptive if the size is good for every space in every subspace of your space that you're considering. Okay, so you want to be adaptive in the size and honest in the confidence. Okay, the problem is that in many infinite dimensional problems, it's not possible. And it sort of dates from a series of papers by Lowe and Kai and Lowe, where they showed in a white noise model, so it's sort of a baby kind of model, where when things don't work in this model, they are not going to work anywhere else. And so that's the first model you have to look at when you study the possibility of or existence of procedures. And it's sort of equivalent to regression and density in some contexts as well. So it's quite a nice model to check as an exercise, but also as a guidelines. So this model corresponds to observing an infinite sequence of observations with an infinite sequence of mean and variance a Gaussian noise with variance 1 over n. So it looks like it's not at all practical, but it's really close to many different models. And so if you have this kind of model, so it's a Gaussian likelihood essentially, what they showed is that if you wanted to have an adaptive confidence region over classes of Sobolev balls, a collection of Sobolev balls, and that were also honest, that it's not possible. You cannot be adaptive in the size and honest in the confidence, or it will get simultaneously. So either you have to weaken the size, or you have to weaken the confidence in the story. And so it's a question of existence. Not that it has nothing to do with being Bayesian. It's really like it's an impossible task to some extent. So what do the Bayesian, where are we in the Bayesian work? In the Bayesian world, as I said, because of this hierarchical construction, you're naturally adaptive. So Bayesians are dishonest because they are optimal in size. They have to be dishonest. They can't be good everywhere. And so the question is now, because you are dishonest, you have to understand where you are honest and where you're not honest. So what are the points for which you get a good confidence, and what are the points for which you're not going to get the good confidence? Okay. And so the aim of the game from now on is to try to understand for some families of priors and families of models what are the points for which you get a good confidence, and if there is a price to pay again there or not. And the starting point of this was a paper by Botond, Savo is here, Harry von Santen and Advan Zervaart, who looked again at the white noise model, because it's a Gaussian likelihood. They considered the Gaussian priors. So each theta j's here are ID Gaussian with mean 0 and variance that decrease to 0 with j at this rate here, like j to the power minus 2 beta minus 1. And then so you have a Gaussian prior. Given beta, you have a Gaussian likelihood, so you have a Gaussian posterior, and you can have explicit computation. And then the question is that if you want to be adaptive, then you have to find a way to choose beta. So you could put a prior on beta, you could put a prior on tau, or you could do maximum marginal likelihood estimation, which is what they did here on beta. So they selected beta hat, that's the value of beta that maximizes the marginal likelihood associated to this model like that. And then from that, they get an empirical base posterior, and they looked at L2 balls associated to the empirical base posterior, where theta hat is the mean. Okay? So that's a sort of simple procedure. They could have put a prior on beta, it wouldn't make a difference in the story. And so when they do that, they have this hierarchical prior, which is like a natural construction. It's, you can prove that you get hierarchical posterior concentration rates, optimal adaptive posterior concentration rate, so the size is going to be correct, which is what I've written here. So for all beta in whatever, and for all theta naught in a subbolus ball with a beta smoothness, then the radius of your ball is of order epsilon n of beta under p theta naught. But then you know that you cannot be honest, but they find out a characterization, or at least a sufficient condition for points for which you are honest. So they found a subset of the parameter space, theta tilde, of good points. So points for which you know that you're going to be honest, or almost honest, because you're going to be honest if you inflate slightly the ball. But what they say is that for any L large enough, then if you are a good point, and I'm going to describe what they mean by a good point, then you're going to have a good coverage for this point. Okay? So what are these good points? So these good points are points in this L2 that decrease to 0 fairly regularly. So you cannot accept very long flat parts where they stay stable and then they decrease, and these flat parts have to go longer and longer as J increases. So these are not acceptable, and they are going to be bad guys. So if you want to be a good guy, and you have to have the decrease of the theta J's that has to sort of be regular in a sense. Okay? And you don't have to describe how regular it is, it just has to be regular. So they have this characterization of the set of good guys for which you have good coverage, and you have good size as well. And the interest here is that these theta tilde is a fairly large set. In other words, they prove that the minimax rates over the theta tilde is the same as over the whole set, and blah blah blah. So there are all sorts of characterizations that says that this set of good guys is actually quite large, and so it's a reassurance because many priors hopefully would tell you the same story. Okay. Now, the problem is that this work was based on Gaussian likelihood, Gaussian prior, Gaussian posterior, and so exact computation. And so our worry when we were looking at that thing is that do we have to always be able to say something on the coverage if you have exact computations? Like, is exact computation the only cases for which you can say something in the story? And so we wanted to have a more general description of the story and to give sufficient conditions so that you can prove that you have good coverage even though you do not have explicit computation. So you don't know explicitly what the likelihood or the posterior distribution looks like. And so that's what we did, but for that we studied the families of prior that have a certain structure. And so you look at the parameter space theta, again, as a collection of finite dimensional spaces, and they are typically embedded in one another. They don't have to be really increasing, but they have to have sort of this structure. And they are finite dimensional, so you can say that dk is equal to k. So for instance, if you take a mixture of k components, then theta k is a mixture of k components, and the whole collection is a families of non-parametric mixtures, or the closure of non-parametric mixture of these sets. Okay, and now so if you have something like that, then the natural way of constructing a prior, where am I here? The natural way of constructing a prior is to select the space where you are in, k, and once you selected k, then to select the parameter theta given k with some whatever distribution on something which is absolutely continuous with respect to the Lebesgue measure, typically. Okay, so that's a hierarchical prior here, and you can either select k using a prior on k, and then you have a fully based procedure, or you could be empirical based by looking at the maximum marginal likelihood estimator for k. So you compute for each k the marginal likelihood, and then you take the k that maximizes the marginal likelihood. They are both going to give you essentially the same result. So you have the fully based or the empirical based, and in either way, once you have that, then you have a posterior distribution, fully posterior or empirical based posterior. And then you can consider a credible ball, again, which possibly you can inflate the radius of the ball, but for the moment forget that. So you have a credible ball around the centering point, like the mean, posterior mean. And the question is, can we say something about the size? So can we say something about the size Rn of alpha in this context, in a general way, generic way? And can we say something of the coverage, a bit like similar to what they had? Can we define sets of good guys for which you have good coverage? Okay. And is this set going to be large? And before I tell you how it works, I'm going to give you the sort of the general ideas behind what's going on. So if you look at the coverage, so if frequent Bayesian coverage, well, the Bayesian coverage, so you're looking at the posterior probability that the distance between theta and your mean is less than t, okay, and t is whatever. This is, you can decompose as the sum over k of the same posterior probability is given k times the posterior probability in k, okay. Now imagine, to make it very, very simple, that theta hat belongs to one of the sets, okay. And now that you restricted yourself to being in this set, then the radius within this set, you know, under a very general condition, that is going to be of order square root of k over n. So if you were in one of the cases, you know exactly what would be the posterior coverage, because you would know the size of the set, or on the order of magnitude of the size of the set. And so really what drives the story is to try to understand what's the posterior probability in k. And that's the key issue here. So if the posterior probability in k is going to behave well, you have a nice coverage. If it's not going to behave well, you're not going to have a good coverage. And so it's a key point here. And now if you think about it, the posterior probability in k is proportional to the marginal likelihood times the prior. And if you sort of remember your first Bayesian class, or maybe second, if you look at the log, and if you had a regular model, a finite dimensional regular model, you would have the BIC formula. And what the BIC formula tells you is that the log marginal likelihood behaves a bit like the minus n times the bias, minus a penalty, which is of order a constant k times log n. Okay? And that sort of BIC formula is a very general formula. Okay? It sort of says that even in non-regular models, even in high-dimensional models, the log marginal likelihood is going to behave to like minus n times the bias, and I'm going to define what the bias means here, minus the constants again, but it doesn't really matter for the constants, times k log n. And so essentially, this thing is going to drive the story in the non-parametric models. And the way you formalize that is to say, so if I write b of k squared to be the bias, which is like for theta naught is in the closure of your space, so it's not necessarily in one of the theta k's. You're looking at the minimal distance for parameter values that are in theta k between theta naught and theta. Okay, so this bias term here. Now what you're going to try to find out is some kind of bias variance trade-off. Okay, and that means that you're going to look at the case for which the bias is of the same order of the BIC penalization. In other words, which is a prior complexity term. It's a bit like the variance trade-off, huh? But it's not the variance, it's a prior complexity term. And so now this K, for which makes a balance between the bias and the prior complexity, are going to be the case on which the posterior distribution is going to concentrate. Okay? So what you can prove is that if you're looking for the minimum value of k such that the bias is smaller than the variance or the prior complexity here, then the posterior distribution is going to concentrate on k for which this epsilon of k like that, which is the sum of the two, is of the same order of the minimum possible value. Okay, and once you have that, then you just have to understand where these k are, and you understand the behavior of the posterior distribution, and then you're going to know whether you have to have good coverage, under coverage, or over coverage, in a sense. And now what you can say exactly the same stories as what they did in the white noise model with Gaussian prior and Gaussian likelihood. But instead of looking at the L2 norm in terms of bias, then you have a bias described by the distance d that you had at the beginning of your story. And so the good guys are the guys for which the parameter values for which the bias is decreasing regularly. Okay, if you have long flat parts, then you're going to be screwed up. And so the posterior distribution is going to concentrate on not the right values of k. And so you're going to have a bias which is larger than the variance, essentially. And so you're going to be overconfident in the posterior distribution compared to the frequentist version of it. And your credible regions are not going to be confidence region. So it's almost there for the general story. So what happens is that if you have under sort of regularity conditions that are the usual one plus something that's slightly less usual but still okay, you can prove that if you inflate a bit your credible region for this sort of generalized Polish tail condition, so the good guys, the frequentist coverage of your credible balls is going to be bounded from below by 1 minus alpha. So you're going to be nicely behaved, and the size of your ball is going to be correct. It's like ln times epsilon n. So I'm saying you have to inflate a bit these balls. And I go back to it because a bit is not so much of a bit, actually. It's a bit more than a bit. So, but before I go into this problem with the ln, I'm going to just give a bunch of examples of models that can be handled like that. And just to sort of give you the flavor of what's going on. So if I work on the density, for example, if I were to estimate the density, and I want to get a credible ball for the density, I cannot, as I said at the beginning, I cannot work with any kind of metric using this kind of theory. You have to have metrics that are well suited, in a way. And typically, the metrics that work well are Hellinger or L1 distances. If I work with the white noise, I can construct balls like that are related to the L2 norm. If I work with a regression, it's sort of essentially the same as the L2 norm. Classification is the average of the Hilligan distances. So what these distances they are what I call statistical distances. So they are distances for which you can make tests that behave well, and so for which you can actually follow the story of Gozal, Gauche, and van der Waals. If you want to work with other distances, then you have to do a lot more work. Now, going back to this square root of log n story, so for the past years of my career, I always thought that log n was constant, and now I have to change this course. Actually, they are not constant anymore. So now I'm getting worried about log n a bit. And yes, I forgot something. So these are the models. So for instance, what you can prove is that you can get nice credible regions that are also confidence regions up to this square root of log n story for regression, density estimation, for these some families of models that look like the one I presented before. So that's just for the example. So I mean, you can derive the stories in fairly general stories, and which is the good news. The bad news is this log n term. So why is it a bad news? It's because somehow, if you could inflate your regions just by an L, large enough, it means that if instead of looking at a 95% credible region, you had looked at a 99% of a credible region, you'd get a good coverage, frequentist coverage. And so you wouldn't have to worry too much about it. Essentially, the order of magnitude of your uncertainty is correct. The fact that here you have to increase the radius as n goes to infinity means that there is an instability behind, and it means that there's something going wrong somehow. It's not hugely wrong, but it's a bit wrong and it's a bit worrying. And so you want to understand whether it's a trick of the proof or whether it's actually really here. And then you want to understand why is that, and because if it's here, maybe there is a reason, and maybe it's good for something, but not for everything, essentially. And so the question that we had with Botond was actually, is this log n really there? Because in a lot of proofs in Bayesian non-parametrics, there are log n's everywhere, and I always kept saying, oh, we don't care about the log n's anyway. But actually, here we want to care about them. And what we showed, the first thing is that if you took the empirical base version of the story, so you choose k by looking at the maximum marginal likelihood estimator, and you look at the credible ball, then you have to have a log n term. If you take anything smaller than the log n term, then the coverage goes to zeros for large families of good guys. That's the problem. They are good guys, and despite the fact that they are good guys, they are still screwed up. And so then it means that the procedure is doing something, and you want to understand what it's doing. Okay? But then you say, oh, well, it's well known that empirical base underestimates the parameter or the uncertainty, and so maybe it's better with the hierarchical base. And the answer is actually no. At least not for so many points. We didn't prove it for the same set of points, but almost. And we're pretty sure it's true for everyone, but it's just harder to prove. And so you can prove that even for the hierarchical base, the posterior distribution is going to underestimate the uncertainty. Okay? And the reason it's underestimating the uncertainty is that it's putting mass on values of k that are too small. Instead, like if you were to have a regularity of order beta, then the sort of optimal value would be n to the power 1 over 2 beta plus 1. And here it's going to be n over log n to the power 1 over 2 beta plus 1. And the reason it's doing that is because is doing that is really because of this BIC story. Yeah? It's because you have this BIC penalty here. And it's the same story. It's exactly the same story as when we say, well, the BIC approach, you are not completely powerful, and you tend to choose models that are too small. And this is exactly the same, but it's a little more crucial here because it's high dimensional, and you want to have the whole parameter. Okay, and so what it does is going to sort of all the small coefficients are going to shrink are going to be put to 0. The large coefficients are going to be perfectly well estimated. You could imagine how to have a Bernstein formulation with given model K. So the large coefficients are going to be perfectly well estimated. You're going to have the right uncertainty on the large coefficients, but you're going to forget completely small coefficients. And that's what all these sort of BIC type priors, so the model choice type priors, do. Okay? And so it's not hugely wrong, but you have to understand that it's there, and if you use these families of prior, then you're going to forget the small coefficients. And you're doomed, in this sense. Not doomed, but it's a bit something like that. So then we were thinking, maybe it's not so bad if you do a linear regression in high dimensions. And the reason we were sort of hoping it wouldn't be so bad is because in linear regression there is a log n there, even in the rate. And so maybe we are not going to have to add another one for the coverage. So let's see how it works. So now if you have a linear regression, so yi equals xi theta plus epsilon I, so the epsilon I are Gaussian, so the usual story here, and xi is in our p, and p is typically larger than n. Now, there are all sorts of prior, like the spike and slab, so families of prior can be done by selecting the size of the non-null coefficients. Once you selected the size of the non-null coefficients, you select the set of non-null coefficients that have size S. And once you have selected the sets of the non-null coefficients, then you put a prior on this coefficient J. Okay, so the spike and slab is a special case of these. Now, there was a really nice series of papers by Ismael Castillo and Ad van der Waart, and then Ismael Castillo and Johannes Schmidt-Eber and Ad van der Waart on these kind of models, and they consider a Laplace slab. So the G that they put on the coefficients is like a Laplace prior. And we extended the story with a fat tails prior, like anything that behaves like that. But the story is still the same. And then for these guys, you can prove posterior concentration rates and all that sort of things for parameters that are sparse. So what I mean by parameters that are sparse is that if I look at large coefficients, so coefficients that would be of order greater than square root of log p divided by square root of n, here the formula is completely wrong, I don't know what I did here. And then so if you look at these guys, then this set of large coefficients has to be small. Okay? So that's what I mean by these sparse sets. So it doesn't mean that you have to be 0 or non-zero. So you have a small number of non-zero. It's slightly more general than that. You have a small number of large coefficients. So the coefficient that you could typically estimate, essentially. And now, if you do that, then the minimax rate of estimating is of order square root of S naught log P over N. And there is a theory on that. And so what you can prove is that these priors, if you put a prior on S which is penalizing enough, then will give you this rate of concentration for the posterior. So you have the right size. Again, so the question is, do you have the right coverage? And now, if you want to study the coverage, the story is slightly more delicate, so it's more difficult. And there is this a series of papers by Edward Belitzer and Botton, Sabo, and some co-authors, and Subashish, and where they looked at good guys again. So they have the story is that you have to find the good guys for which it's possible to have good coverage and good size, because again, it's the same story. You cannot be both good in everything. You have to lose somewhere. And so the good guys in this case are points for which you can make a trade-off between bias and variance, essentially. And so what you can prove is that if you put the sort of prior on S which penalizes enough, and the regularity condition on the model, on the covariance matrix, on the X matrix, the design matrix, then you get the right concentration rates, and you also have a local Bernstein from this result. In other words, for all S that are under the support of the posterior distribution, you're going to have a nice, really behaved conditional distribution, posterior distribution on theta given X and S. So you think, oh, if I have a local Bernstein families, I should be good. But unfortunately, the posterior distribution of S given Y is actually is again driving the whole story. And it's not always well behaved. And you have the same sort of things, is that it's going to be good if you inflate the radius again by a log n term. So you still have this sort of damned log n terms that come in. And the question that we have is, are these log n terms here, or are they just an artifact of the proof? And what you can prove is that if you take a prior that sort of are the prior that were proposed by Ad and Ismail in some part of the paper, where you have I'm going to skip the details, where you have a strong penalty on S on the size, then you're going to have the square root of log n inflation in order to have good coverage. So you do have this log n term that pops in for parameters that have large coefficient and a large number of very small coefficients. And so if you have a very large number of very small coefficients, these ones are going to be completely forgotten by your prior, because they are going to be put to 0. And so the posterior distribution is going to be good for the large coefficient, again, but forgetting completely the small coefficients. And so for the L2 norm on the whole set of parameters, it's not going to be good, because the L2 norm is strongly influenced also by the small coefficients, because you have a large number of them. Okay? And so all these points are going to be badly represented in terms of uncertainty with your prior model. Now, there are lots of questions that come in. And it's all ongoing work. And don't get out of this room thinking, Bayesian doesn't work. It's not true, actually. It works, but you have to be careful about the way you construct your hierarchy. What sort of comes out of this story, I mean, it's funny, there are all sorts of subtle things coming in. For instance, if you take a spike and slab, so you have your spike and slab is like you choose a non-zero coefficient with parameter omega, and 0 with probability 1 minus omega, and you choose a maximum marginal likelihood distribution on omega, or you put a prior on omega. If you do something like that, then you're going to have really good coverage and good size as well. So this one is the right way of doing the hierarchy in a sense. And also, if you consider a continuous, at least it's been proved in the sequence model, which is a baby version of the linear regression model. But it's very true for the linear regression model. If you take the horseshoe prior, for instance, which is a prior that was considered in the literature, which is a continuous prior on theta. So you don't have zeros and non-zeros, but you have small and large. This one, for the horseshoe, you get also good coverage and good size as well. But from the computation and its ongoing work, what it seems is that if instead of so the horseshoe is a hierarchical prior. You have a Gaussian and you put some prior on the sigma squared, on the variances that are the Cauchy prior for the sigma squared. If you take anything that's lighter than Cauchy, then you don't get the right results apparently. So you don't get the right coverage. So there are really like subtle things going on in these kind of high dimensional models. And you can't really make any generalization from one prior. You have to study things carefully to make sure that what you're doing is correct. What it seems to be true is that for any large coefficient are going to be well estimated, it's the small ones that you have to be worried about. If you have to be worried about, maybe you don't care about those ones. So that's sort of the conclusion. Thank you.